to put a marker in. All right, so we're going to be continuing the bytecode chapter. We are almost halfway through it, so we'll see whether or not we get all the way through it today, or if we have to like continue into tomorrow with it too. This is a fairly large chapter, but we're also apparently creating our own language, so that's cool. We're continuing off at this specific point right here. So in the yesterday, we ended up creating this class that has the push and pop methods. And so now we're going to start when the instruction needs to receive parameters. It pops them off of the stack. So we have these methods here. And here's our interpret method. And so our switch, which is going through our instructions. And we have our cases. And so, okay, if we have like set health, we need to pop off the stack information. So theoretically, we pushed a value on, and now we want to pop it off. So in amount Oh, that was fun. Katali, hello! Good morning! Let's see. Okay, so basically we can get the amount here and this dot pop. So pop off the stack there. Oh, interesting. So the idea is that the amount and the wizard are going to be in the specific order that they're put in. It's like amount first, wizard second, or is it the other way around? I can't remember. Const wizard equals this dot pop. And then we could have wizard amount. Okay. And then, I mean, basically that's going to be the exact same thing here, right? So in instruction enum set wisdom, it's going to be the same as this. So we're going to do const wizard equals this dot pop. Const why am I not getting any color coding on this? Const amount equals. Oh, because I forgot the colon like that. Okay, then this dot pop, and now you can be wizard and amount. Okay. I mean that makes sense. In these like place sounds, it's just like the sound ID coming off, the particles, the particle ID coming off. Okay, I mean that makes sense. To get some values onto that stack, we need one more instruction, a literal. It represents a raw integer value, but where does it get its value from? How do we avoid some turtles all the way down infinite regress here? The trick is to take advantage of the fact that our instruction stream is a sequence of bytes. We can stuff the number directly into the byte array. We define another instruction type for a number literal like so. So instruction literal value bytecode push value. Okay. So get the value from the bytecode. So here's where's bytecode? Okay, so bytecode is set to this. Interpret Oh, I don't think we ever call interpret ourselves. So I guess bytecode plus plus, but why are we pushing? Okay, I don't know why we're pushing something on, but let's say we do that case. So, okay, some kind of like instruction literal. So these cases are here. So I guess I'm not really sure why we're just taking something off of this array that's coming in and then just pushing it back. Oh, it's pushing onto the stack. Okay, got it. That's what's happening. I was misthinking that this is the stack, but no, it's not. So if we do this, then we have const value equals bytecode. Now this is basically, we're in a for each here. So we already have BC right here for the bytecode. So we can just push that. So it's going to be this dot push BC. I mean, that's pretty much it. Pretty simple. Here I'm reading a single byte for the value to avoid the fiddly code required to decode a multiple byte integer. But in a real implementation, you'll want to support literals that cover your full numeric range. So literal 0x0s or 5 or whatever, that's supposed to be value 1, 2, 3. It reads the next byte in a bytecode stream as a number and pushes it onto the stack. Let's string a few of these instructions together and watch the interpreter execute them to get a feel for how the stack works. We start with an empty stack and the interpreter pointing toward the first instruction. So if we have an empty stack. Okay, so if we do something like our stack, there's nothing here right now. And the interpreter, so literal. So we do this literal. First it executes the first int literal. That reads the next byte from the bytecode and pushes it onto the stack. Oh, I see. So my entire method of doing this for each here is now we can't do that. Okay. I see what they're going for here. So this can't be, we're gonna have to have some kind of, just like they had a counter, like an incrementer. So we'll have to have something like a let index equals 0. We're not gonna for each through this, which means that this doesn't happen either. Now, when we come through this, and so it's going to be the bytecode of position index, right? Okay, yeah. So for set health, set wisdom, we're not even touching the index at all. we're just getting the instruction. Where did that thing go? I mean, I'm assuming that's where this is, but okay, so we interpret our bytecode, which is an array of these bytecodes. We have the index of this. I guess we have the instruction, the current instruction. So const instruction equals bytecode of position index. Okay, so if we do that, then this becomes the instruction. So we're going to put into the bytecode the results of like these enum. These enums are just whatever. We don't really care anymore. It just becomes, okay, we just want to get the instruction out of there. We switch on this instruction. If the case is set health, then pop off the amount, pop off the wizard, and then set health. If the case is set wisdom, do the same thing for wisdom. If the case is this instruction literal, so this is where we want to increment I, because we need to go to this next one here and read that in. So the first thing we do is index plus equals to 1. Then push the bytecode of position index. Then I assume that we're having to loop through this in some way. I don't think they're showing us. Where is the interpret? Okay, yeah, so this is a full for loop that we have going here. So it's not just this. This will be a for loop. So for let index equals 0, index is less than is that the reason why we have a separate size? Because it allows us to control index separately? Or can I just do I have size in here? I do. Okay, so I could then do this size. Then this entire switch comes up into here. And so then we're increasing index early to go to the next one. And then we can push the result of that onto the stack. So we look at our literal. So here we get our instruction literal. We increase our index to here, and then we push that onto the stack. So now we have 0 on the stack. Then we hit this literal, which is this again, and 10. So now it pushes 10 onto the stack. And then the next one is health. So it hits this health. It pops amount off. So amount becomes 10, and this goes away. I mean, and then theoretically the next one will be, oh no, it pops 10 off, then it pops 0 off. So the stack is now empty, and now it sets the health of the wizard, and then we're done. There's no more in this array, so the for loop ends. And all the things that we're going to be done is done. Whew. First executes, then it reads the next byte from the bytecode, 0, and pushes on stack. Then it executes the second interliteral, then it reads 10 and pushes that. Okay. Finally, it executes int set health. That pops 10 and stores it in a mount. Then pops 0 and stores in a wizard. Then it calls set health with those parameters. So the order of this is incredibly important. Like, we don't have anything where it's like, hey, it could be anything. Good luck. Ta-da, we've got a spell that sets the player's wizard's health to 10 points. Now we've got enough flexibility to define spells that set either wizard stats to whatever amounts we want. We can also play different sounds and spawn particles. But this still feels like a data format. We can't, for example, raise a wizard's health by half of their wisdom. Our designers want to be able to express rules for spells, not just values. Behavior equals composition. If we think of our little VM like a programming language, all it supports, oh, I guess, hold on, before we do that, we're doing the Rust stuff. Let's go implement this in Rust. So we have our VM, we have our interpret, which is matching off of our instruction set. We're no longer gonna be able to do this simple bytecode. So in our struct VM, we're gonna need to store, let's go back to the beginning of this. Yeah, we're gonna need to store our stack size, not necessarily that. Oh, right, because we need our stack now. So if we have, for example, a stack, if I set this to be an array, I have to set like the amount of it, and then what's gonna go inside of it. Well, it sounds like it's gonna be instructions go in it. Is it instruction? I think it is instructions. Or is it just, it's just numbers. So these are gonna be like I32s. And is it semicolon? And then the number of them. So this is gonna be our stack size, which we're setting this to be 128. So 128. Oh, I have to set that here, don't I? So we have a max stack, which is I32. Yeah, I don't think I can I have to say at this point in time what this is going to be. I can't just say like, hey, this is going to be an I32. It knows that. We have our stack size. Then we have the stack itself. And then the current stack size. So stack size, which is an I32. Now we might as well implement this VM and add in a new function. So pub function new, just to make this a little bit easier. We're not like, we just need to initialize it really. So this returns a VM. So we are going to return a VM that has a stack. I mean, can I do that and it figures out what that's supposed to be? Our max stack is going to be 128, and our stack size starts at 0. I mean, it's not yelling at me, so this probably compiles and then this works. So then we come along here and now we add in our push and our pop methods. Okay, so pub. Oh, these are going to be private that are going to be used by the interpret here. So we have just function push, which takes mute self and a value, which this entire thing is based upon i32s. We're not going to return anything. We're just going to say self dot stack of position stack size. Oh, we have to first check for overflow. Right. Because in here we're working with like more traditional arrays where we can't like control this. So I don't know if I can do an assert. So in this case, we'd want to return a result. And the result, I can never remember, is it error? Oh, it's the type and the error. So it's going to be nothing if it's successful. And then the error is going to be, probably we'll just do like a static string. How do I do? Like that, I think. Hold on, let's do it. No. There we go. Okay, so it's going to be a static string that we return from here. So then, public mute self, we want to double check that we're, that if we increase our stack size, because we're starting with 0, so let's go ahead and do that first. So self dot stack size plus equals to 1. I guess I don't want to do that now. Okay, I want to check first. So if self.stack size, if that is greater or equal to self.max stack. Okay, so if we're at the end already, then we want to return an error. And it's going to be specifically this static string. So return error, and then we get to just put this static string in here, which is stack size. I mean, we could just go like stack overflow. Now, if we get to this point, we're okay. So we can now do self.stack size plus equals to 1. And then we can add into this stack. So it's going to be self.stack of position self.stack size equals the value. And then return okay. Like that. Okay. A little bit more complicated than the JavaScript side, but one should expect that when we're working with, like, you know, a much more systems level programming for this type of stuff, at least. I haven't really worked with arrays very much. That's super interesting. Next, the thing that we're going to do is the pop. So we have to make sure that the stack isn't empty. But then we can just return whatever is on there. And also we have to update the stack size. So then we're going to have function pop mute self. We're not going to have a value. This just returns. So here is going to be a little bit more interesting. We're going to have the result, which we return in i32, or for the error, we have a static string. Now, that's mostly because I'm not like, it might actually be easier, and I've seen this before. We could have an enum like errors. So like, I don't know, custom errors. And so like one of these errors could be stack overflow, like that. And then we can come down here and we'll say, okay, well, instead of this static string, we're actually going to return a custom error. And so the error is custom error stack overflow. So here, what's our error that we can get? Stack underflow. Okay, so first thing we want to do, make sure that we're not at 0 already. So if self.stackSize is already equal to 0, then we're going to return error, which is our custom error stack underflow. However, if we're not at 0, that means we're clearly 1 or above. I could also check if we're less than 1. Then reduce stack size, so self.stackSize minus equals to 1. And then we're going to return as part of this result. So we're going to say, okay, and we're going to return self.stack of position self.stackSize. All right, there is push and pop. When an instruction needs to receive parameters, it pops them off the stack. Okay, so now we can update interpret here. So it's not just setting health. Now we need to do a little bit more interesting things here. Which also means that we can't just do this for loop quite exactly like this. It's going to be similar. So we're going to say for index in, and then we're going to do a range. So it's going to be 0 ... self stack size, which is that inclusive? I think I need this to be inclusive, don't I? Did they do theirs as inclusive? Where's their for loop? Theirs is not inclusive. I guess I'm trying to think about it, like how the index increasing or not. I think, well, let's do it just like the way they have it, which is not inclusive. So for index in 0 through this, so it's going to increment through here. Now, when we do our set health, the first thing we need to do is we need to pop off the amount and then the wizard. So we're going to say let amount equals self. Okay, so then this needs to be mute now. So self dot pop let wizard ID equals self dot pop. And the order that we do this here, this is just, we have to tell the designers, this is the order you do it in. If you don't do this order, everything screws up. And then we can now do a set health. Hand it the wizard ID and the amount. Just like that. And it's going to be the exact same thing for here. So I can even, let's copy you, paste you in, and this is going to be set wisdom. And then the wizard ID and amount. All right. And so I think this this updates to it. I kind of like the Rust version more because these, like actually having the enums helps out a lot. And so if we flow through here again, let's say we have the byte codes that we pass in is going to be these this array of instructions, which is going to be a little bit interesting, right? Because this array of instructions is not the same as our stack, which I think I initially got a little bit confused with. So we're going to have like literal. Oh, so we have to add in literal, don't we? So we're going to have what did they call it? Literal, instruction literal. So instruction, which like doesn't really mean much, with like add next, like maybe what we should add into here. I'm not exactly sure what we want to do in, but add next. So, okay, add next is gonna be here. Instruction, add next. We are going to push we're now going to push the onto the stack. So, oh, we can't do self.pop here because we got results. We've got to handle those. The easiest way to handle a result is just to question mark this. And that will give us the amount, if there is one. Now, of course, that means we now have to have a return value of the result, sort of like just to push that up the stack all the way up to the top to bubble up our errors. Okay, so with add next, we're going to take in the next thing. So we're just going to say index plus equals to 1, like that. Now, I don't know if index is mutable or not. I think I need to make it mute. Then once I do that, I can now we're going to push onto the stack whatever is on there. So we're going to say self.push, and then it's going to be the byte codes of position index, like that. And I don't think there's anything else that we really care about. Oh, the match off of this is going to have to be the instruction. So we're going to have to get the byte code. So let byte code equals byte codes of position index. So, okay, so that gives us our byte code. Then we can match off of that. The easiest thing to do here is actually just straight up match off of that. Then we do our stuff. We handle these errors, which means we need to return. This is going to be a result. We're not returning anything, so the OK is just an empty parentheses, and then the error is our custom error, which means down at the bottom here we now need to return an OK, like that, and then this will be fine. And self.push, we're also going to handle the error like that. Okay, I think that's it. So we get our instructions, which is going to be, what is it? Set health 0, what do they put it as? 0 and 10 and health. So we're gonna push on. Oh, interesting. So the way this is working here, it can't just be an instruction like this. So with the enums in Rust, it's a lot easier for us to do something like this. I32. I32. You know, this would be so much easier for us to like make this I32 I32 like a tuple. We don't even need an add next anymore. This by doing it this way, we skip the entire stack system. If we really wanted to use a stack, then it would be add next, where we do I32 like this. Or just going to be like I32, and then we go there. But if we actually want to make it our own, we would like to do this the Rust way. We don't need an add next. We just need set health and set wisdom. Set these to here. We don't need any of this stack stuff, which means we don't need the new. We don't need even push and pop anymore. Like this just isn't necessary for the type of system we have, simply because Rust gives us these special enums. So now we're gonna have our instructions. We can go back to our mute. So our for byte code in byte codes. We're gonna match byte code. If we have the instructions set health, we don't need to do any like this pop stuff. But we do need to do is catch the values. So this is going to be the wizard ID, and this is going to be the health or the value. Oh, I think you can hear that. That's garbage truck right outside. It'll be gone in a second. And then we don't even need this add next. This is pretty much what it becomes. Super simple, and that's only because when we're pushing onto the stack, we can have enums that store a little tiny bit of data like this. And now it becomes incredibly easy to sort of see what's going on. All right, they're down. They're at the neighbors now, so I don't think it's going to be caught by my microphone as much. I have the windows open because it's nice to have like air flowing in because I closed the door. Okay, so I think that's what it is. So now if we have, when we pass in this array with the Rust code, instead of this like literal 0, we're just going to say, give us interpret, give us the health 0, 10. And then it just does it. Like very, very, very simple. All right, behavior equals composition. If we think of our little VM like a programming language, all it supports now is a couple of built-in functions and constant parameters for them. To get bytecode to feel like behavior, what we're missing is composition. Our designers need to be able to create expressions that combine different values in interesting ways. For a simple example, they want spells that modify a stat by a certain amount instead of to a certain amount. That requires taking into account a stat's current value. We have instructions for writing a stat, but we need to add a couple to read stats. Okay, so we have this instructions get health. Okay, so then there's going to be like get the health of the wizard. So pop the wizard ID, push get health wizard. It would be hard to complain about the garbage truck noise when they at least keep going while half the country shuts down. That is true. They've only taken time off for the holidays, which we don't like. We give them 10 a year, so that's not even very much. Okay. So we're gonna get the health and then push that out. So like that's where this function potentially get health comes in. And we break. Get wisdom, get agility. Okay, you get the idea. As you can see, these work with the stack in both directions. They pop a parameter to determine which wizard to get the stat for, and then I look up the stats value and push that back onto the stack. This lets us write spells that copy stats around. We could create a spell that sets a wizard's agility to their wisdom, or a strange incantation that sets one wizard's health to mirror his opponent's. Better, but still quite limited. Next, we need arithmetic. It's time our baby VM learned how to add 1 plus 1. We'll add a few more instructions. By now you probably got the hang of it, and you can guess how they look. So this sort of feels like then we're gonna write in like the equivalent of assembly, right? So is the instructions for this, like the custom language, is it gonna look like add, I guess like add health, something so we can parse through the code here pretty easily, and we can say like, okay, add health, wizard ID like 0, 14 health, something like this. But it wouldn't just be like add health 14. It would maybe be like where we want to now do like the other wizard's name. So we need to like get the health of the other wizard, and then do that. That seems a little bit interesting. I'm curious about like how it's all going to come together at the end. Which then maybe what I should do is just read through the entire chapter, and then we can sort of rebuild this. Because it looks like it's going to be a little bit more complicated. Of course, creating a language, of course, a little bit more complicated, of course. So let's try that. Let's try actually just finishing the chapter and then seeing where it's going. These work with the stack in both directions. They pop a parameter. So, okay, now we need arithmetic. So now we need this case instruction add. So we're going to add that in to our enum. We have A, so pop the two, A and B, and then push the results of adding them together onto the stack now. Like our other instructions, it pops a couple of values, does a bit of work, and then pushes the results back. Up until now, every new instruction gave us an incremental improvement in expressiveness, but we just made a big leap. It isn't obvious, but we can now handle all sorts of complicated, deeply nested arithmetic expressions. Let's walk through a slightly more complex example. Say we want a spell that increases the player's wizard's health by the average of their agility and wisdom. In code, that's set health 0, get health plus, then get agility plus wisdom, and then divided by 2. You might think that we need instructions to handle the explicit grouping that parentheses gives you an expression here, but the stack supports that implicitly. Here's how you can evaluate this by hand. Get the wizard's current health and remember it. Get the wizard's agility and remember it. Do the same for their wisdom. Get those last two and add them, then remember the result. Divide that by 2 and remember the result. Recall the wizard's health and add it to their result. Take that wizard and set. This is very they're getting this ready to code in assembly. Not good assembly, our own assembly, but that's sort of what it feels like. Do you saw all those remembers and recalls? Each remember corresponds to a push, and the recalls are pops. That means we can translate this to bytecode pretty easily. For example, the first line to get the wizard's current health is literal 0, get health. This bit of bytecode pushes the wizard's health onto the stack. If we mechanically translate each line like that, we end up with a chunk of bytecode that evaluates our original expression. To give you a feel for how the instructions compose, I've done that below. To show how the stack changes over time, we'll walk through a sample execution where the wizard's current stats are 45 health, 7 agility, and 11 wisdom. Next to each instruction is what the stack looks like after executing it, and then a little comment explaining the instruction's purpose. Okay, yeah, this. Okay, so literal 0, so we add on 0 to the stack. Literal 0, so we add on that. Get health. Is get health pushing onto the stack? I think that is. Literal 0. Oh, interesting. So these is wizard index, wizard index. These are like the two different components. So get health of the last wizard index. So the first one is still there. Literal 0. Then another wizard index. Get agility for this wizard index. So now that's 7. Literal 0, the wizard index again. Get wisdom. We add those two. Okay. It adds these two together, which is the agility and the wisdom. And that gives us 18. Literal 2. Divide these two. Okay, so then we get 9. Then we add 9 and 45. So we just added to our health. Oh, that is complicated. That's all for the same wizard. If you watch the stack at each step, you can see how the data flows through it almost like magic. Haha. We push 0 for the wizard index at the beginning and it just hangs around at the bottom of the stack until we finally need it for that last set health at the end. Maybe my threshold for magic is a little bit too low here. Okay, so if we go backwards, well, I still not sure that like this way isn't like the way to go about it. A virtual machine. I could keep going, adding more and more instructions, but this is a good place to stop. As it is, we've got a nice little virtual machine that lets us define fairly open-ended behavior using a simple, compact data format. While bytecode and virtual machines sound intimidating, you can see they're often as simple as a stack, a loop, and a switch statement. Remember our original goal to have behavior be nicely sandboxed? Now that you've seen exactly how VM is implemented, it's obvious that we've accomplished that. The bytecode can't do anything malicious or reach out into weird parts of the game engine because we've only defined a few instructions that touch the rest of the game. We control how much memory it uses by how big of a stack we create, and we're careful to make sure it can't overflow that. We can even control how much time it uses. In our instruction loop, we can track how many we've executed and bail out if it goes over some limit. Controlling execution time isn't necessary in our sample because we don't have any instructions for looping. We can limit it in execution time by limiting the total size of the bytecode. This also means our bytecode isn't Turing complete. There's just one problem left: actually creating the bytecode. So far, we've taken bits of pseudocode and compiled them to bytecode by hand. Unless you've got a lot of free time, that's not going to work in practice. Also, like the game, I mean, how's that going to work? It's like, okay, this is a turn-based game. Mail your command to the devs at PO Box, and they will respond with a little bit of code that you add into your game, and it will update the game state. Spellcasting tools. One of our initial goals was to have a higher level way to author behavior, but we've gone and created something lower level than C++. It has the runtime performance and safety we want, but absolutely none of the designer-friendly usability. To fill that gap, we need some tooling. We need a program that lets users define the high-level behavior of a spell and then takes that and generates the appropriate low-level stack machine bytecode. That probably sounds way harder than making the VM. Many programmers were dragged through a compilers class in college and took away from it nothing but PTSD triggered by the sight of a book with a dragon on the cover or the words Lex and Yak. I'm referring, of course, to the classic text, compilers, principles, techniques, and tools. In truth, compiling a text-based language isn't that bad, although it's a bit too broad of a topic to cram in here. However, you don't have to do it. What I said we need is a tool. It doesn't have to be a compiler whose input format is a text file. On the contrary, I encourage you to consider building a graphical interface to let users define their behavior, especially if the people using it won't be highly technical. Writing text that's free of syntax errors is difficult for people who haven't spent years getting used to a compiler yelling at them. Instead, you can build an app that lets users script by clicking and dragging little boxes, pulling down menu items, or whatever else makes sense for the kind of behavior you want them to create. My company, I'm not on like the game side. It's not really a game. It's the simulation side of the company. But the Unity developers there have created a basically this entire scenario builder is what they're calling it. And anybody can go in and then create the scenario, and that just creates this god-awful JSON object that then gets read into Unity and then builds out. It then reads that to figure out like, okay, what is it going to do? When is it going to do it? How is it going to do it? And I've seen the scenarios. They are really complex. So it's very nice to have a graphical interface for it. So I definitely see this. JavaScript would be great for designing these, even for REST code, which I wouldn't necessarily use if it's just purely Rust that's going to run this. Yes, I could use Serde JSON, but there's also RON, Rust Object Notation. I haven't played around with that, so that might be interesting. The scripting system I wrote for Henry Hotsworth in a puzzling adventure worked like this. Okay, so called check counter. If count is 60, call increment, delay 240 frames, play sound TikTok. On trigger, send despawn to minions. Okay. The nice thing about this is that your UI can make it impossible for users to create invalid programs. Instead of vomiting error messages on them, you can proactively disable buttons or provide default values to ensure that the thing they've created is valid at all points in time. I want to stress how important error handling is. As programmers, we tend to view human error as a shameful personality flaw that we strive to eliminate in ourselves. To make a system that users enjoy, you have to embrace their humanity, including their fallibility. Making mistakes is what people do, and is a fundamental part of the creative process. Handling them gracefully with features like undo helps your users be more creative and create better work. This spares you from designing a grammar and writing a parser for a little language. But I know some of you find UI programming equally unpleasant. Well, in that case, I don't have any good news for you. Ultimately, this pattern is about expressing behavior in a user-friendly, high-level way. You have to craft the user experience. To execute the behavior efficiently, then you need to translate that into a lower-level form. It is real work, but if you're up to the challenge, it can pay off. This also reminds me, a lot of those like programming games, when they don't want you to be able to write your own language, they provide some kind of usually graphical language. So I'm thinking Scratch, for example, several of those puzzle programming games. What's like one of the big ones? It's where you're like in the big like a company, Human Resources, I think. That game has you like programmed by dragging around instruction sets. That's literally this. So that's actually pretty cool. Design decisions. I tried to keep this chapter as simple as I could, but what we're really doing is creating a language. That's a pretty open-ended design space. Exploring it can be tons of fun, so make sure you don't forget to finish your game. Since this is the longest chapter in the book, it seems I failed that task. How do instructions access the stack? Bytecode VMs come in two main flavors, stack-based and register-based. In a stack-based VM, instructions always work from the top of the stack, like in our sample code. For example, instruction add pops two values, adds them, and pushes the result. Register-based VMs still have a stack. The only difference is that instructions can read their inputs from deeper in the stack. Instead of instruction add always popping its operands, it has two indexes stored in a bytecode that identify where in the stack to read the operands from. With a stack-based VM, instructions are small. Since each instruction implicitly finds its arguments on top of the stack, you don't need to encode any data for that. This means each instruction can be pretty small, usually a single byte. Code generation is simpler. When you get around to writing the compiler or tool that outputs bytecode, you can find it simpler to generate stack-based bytecode. Since each instruction implicitly works from the top of the stack, you just need to output instructions in the right order to pass parameters between them. You have more instructions. Each instruction only sees the very top of the stack. This means that to generate code for something like A equals B plus C, you need separate instructions to move B and C to the top of the stack, perform the operations, and then move the result into A. With a register-based VM, instructions are larger. Since instructions need arguments for stack offsets, a single instruction needs more bits. For example, an instruction in Lua, probably the most well-known register-based VM, is a full 32 bits. It uses 6 bits for the instruction type, and the rest are arguments. The Lua folks don't specify Lua's bytecode format, and it changes from version to version. What I'm describing here is true as of Lua 5.1. For an absolutely amazing deep dive in Lua's internals, read this. This it goes to Lua Forge. Oh, okay. Lua Forge is their documentation / wiki. So they have an entire sort of like introduction to 5.1's bytecode internals. You have fewer instructions. Since each instruction can do more work, you don't need as many of them. Some say you get a performance improvement since you don't have to shuffle values around in the stack as much. So, which should you do? My recommendation is to stick with a stack-based VM. They're simpler to implement and much simpler to generate code for. Register-based VMs got a reputation for being a bit faster after Lua converted to that style, but it depends deeply on your actual instructions and on lots of other details for your VM. What instructions do you have? Your instruction set defines the boundaries of what can and cannot be expressed in bytecode. and it also has a big impact on the performance of your VM. Here's a laundry list of the different kinds of instructions you may want. External primitives. These are the ones that reach out of the VM into the rest of the game engine and do stuff that the user can see. They control what kinds of real behavior can be expressed in bytecode. Without these, your VM can't do anything more than burn CPU cycles. Internal primitives. These manipulate values inside the VM. Things like internals, arithmetic, comparison operators, and instructions that juggle stack around. Control flow. Our example didn't cover these, but when you want behavior that's imperative and conditionally executes instructions or loops and executes instructions more than once, you need control flow. In the low-level language of bytecode, they're surprisingly simple: jumps. In our instruction loop, we had an index to track where we were in the bytecode. All jump instruction does is modify that variable and change where we're currently executing. In other words, it's a go-to. You can build all kinds of higher-level control flow using that. Abstraction. If your users start defining a lot of stuff in data, eventually they'll want to start reusing bits of bytecode instead of having to copy and paste it. You may want something like callable procedures. In their simplest form, procedures aren't much more complex than a jump. The only difference is that the VM maintains a second return stack. When it executes a call instruction, it pushes the current instruction index onto the return stack and then jumps to the called bytecode. When it hits a return, the VM pops the index from the return stack and jumps back to it. Okay, so it's like going back and forth. How are values represented? Our sample VM only works with one kind of value, integers. That makes answering this easy. The stack is just a stack of ints. A more full-featured VM will support different data types, strings, objects, lists, etc. You'll have to decide how those are stored internally. A single data type. It's simple. You don't have to worry about tagging, conversions, or type checking. You can't work with different data types. This is the obvious downside. Cramming different types into a single representation, think storing numbers as strings, is asking for pain. A tagged variant. This is a common representation for dynamically typed languages. Every value has two pieces. The first is a type tag, an enum, that identifies the data type is being stored. The rest of the bits are then interpreted appropriately according to that type, so we have value type, int double string, and then our value type union, int value, double value, string value. Values know their type. The nice thing about this representation is that you can check the type of value at runtime. That's important for dynamic dispatch and for ensuring that you don't try to perform operations on types that don't support it. It takes more memory. Every value has to carry around a few extra bits with it to identify the type. In something as low level as a VM, a few bits here and there add up quickly. An untagged union. This uses a union like the previous form, but does not have a type tag that goes along with it. You have a little blob of bits that could represent more than one type, and it's up to you to ensure that you don't misinterpret them. This is how statically typed languages represent things in memory. Since the type system ensures at compile time that you aren't misinterpreting values, you don't need to validate it at runtime. This is also how untyped languages like assembly and Forth store values. Those languages leave it to the user to make sure they don't write code that misinterprets a value's type. Not for the faint of heart. Of course, that's like JavaScript too. It's compact. You can't get any more efficient than just storing the bits you need for the value itself. It's fast. Not having type tags implies you're not spending cycles checking them at runtime either. This is one of the reasons statically typed languages tend to be faster than dynamic ones. It's unsafe. This is the real cost, of course. A bad chunk of bytecode that causes you to misinterpret a value and treat a number like a pointer or vice versa can violate the security of your game or make it crash. If your bytecode was compiled from a statically typed language, you might think you're safe here because the compiler won't generate unsafe bytecode. That may be true, but remember that malicious users may handcraft evil bytecode without going through your compiler. That's why, for example, the Java virtual machine has to do bytecode verification when it loads a program. So we'd have to like verify it at runtime, which like cert JSON does, for example. So if I use JSON, I could definitely like do that kind of verification. And interface. The object-oriented solution for a value that may be one of several different types is through polymorphism. An interface provides virtual methods for the various type tests and conversions. Along the lines of, okay, so we have a class value. We don't do anything in its constructor. A value type interface. Okay, so type returns a value type. Virtual, so as int returns an int. Assert false can only call this an int. Return 0. I guess this is a virtual, so it's gonna be overridden. Fanks Games is rating with a party 41. Thank you so much, Fanks Games, and welcome everybody. Welcome, welcome, welcome. We are going through and we're reading through the Bytecode chapter of game programming patterns. We are. I was doing a bunch of the code to sort of write the interpreter for this, and do that. Now, let's see. Fanks Games. Can I actually see your channel on this? Let me go into Fanks Games. What was your stream about, Fanks Games? And how was it? Indie game developer wants to develop an online multiplayer retro RPG in AS3 and Node.js. Awesome! That's pretty cool. Also, I tried to mute that and I didn't. So copy you. You can check out Fanks Games here. Massively on my pixel art game dev. Awesome, awesome, awesome. Well, that's great, and thank you again for the raid. For everybody, what we've been doing here is I've been reading through this book, Game Programming Patterns.com, by Robert Nystrom. We are on. This book is available where you can actually go in and read the book online for free or purchase it. We've gone down all the way to the Bytecode chapter here. And the Bytecode chapter is apparently where you create your own language. So the idea for this is you're creating a language that your game designers can then sort of, they write in that language. And then you can write your game engine and like the game, and then they sort of work together to actually do whatever you want to do. I'm planning on writing an infinite runner that sort of implements everything that I used here. And I'm not exactly sure if this bytecode, like creating a language for that, I don't know if I'm going to be complex enough to make it worthy of having this other language. But other games, maybe in the future. So I'm going to have to keep this in mind for future things. I've also been doing examples for these codes, both in JavaScript and Rust, because I do a lot of Rust on this channel. And so we're way down here near the end of it. So I've just been reading through this to begin with and sort of like figuring out all the code in here is in C++, which I'm not familiar with myself. Seems like that would have, yes, absolutely. So like they did mention at the beginning of this chapter that this is huge for games that are moddable. Like you want people to be able to mod the game, give them this extra language that's pulled in by the compiled code and then run that way. That way you don't have to like give them the compiler and have them recompile the entire engine every time they want to like make a little tiny change. RPG would benefit from this probably, like to set up entity interactions and maybe monster AI. Absolutely. Or I was thinking like something like Minecraft. Minecraft was famously very moddable. I guess is, right? If you want to add a monster, you don't have to go into the original Java code, you have to write in this other language that they have, which gets pulled in by the core engine, and then that adds in a monster. It changes all of the graphics, or it like updates your health and like makes it different. You can do all those different things through this a different language, which would be like this, which is really, really, really cool. I've never made a game complex enough that would require this, so I'm hoping like maybe there's like a demo thing that I can do that would require this, and that would be really cool. Okay, so basically this would be an interface class that has this type and asInt. Also, this entire bytecode that the author is going through is only bytecode for integers. Like it doesn't handle other types. Then you have concrete classes for each specific data type. Like, okay, so then we're gonna have our int value class that inherits from value. So in our constructor, just call super essentially and pass in the value. Oh no, we're going to store the value internally. Like that. Okay, so then value type. So now we're going to implement these methods here. Return int type. Well, okay, return int type, which is, or type int. Where is type int stored? Is that just a global that's somewhere? I think that is. And then as int, return the value as an integer. Okay. So it's open-ended. You can find new value types outside of the core VM as long as they implement the base interface. That's what this is. It's object-oriented. If you adhere to OO principles, this does things the right way and use polymorphic dispatch for type-specific behavior instead of something like switching on a type tag, which is what we were doing basically over here. If we look at this interpreter here, we have to switch on the instruction set that's coming in. It's verbose. You have to define a separate class with all the associated ceremonial verbiage for each data type. Note that in the previous examples, we showed the entire definition of all the value types. Here we only cover one. It's inefficient. To get polymorphism, you have to go through a pointer, which means even tiny values like booleans and numbers get wrapped in objects that are allocated on the heap. Every time you touch a value, you have to do a virtual method call. In something like the core of a virtual machine, small performance hits like this add up quickly. In fact, this suffers from many of the problems that caused us to avoid the interpreter pattern, except now the problem is in our values instead of our code. My recommendation is that if you can stick with a single data type, do that. Otherwise, do a tagged union. That's what almost every language interpreter in the world does. The next garbage truck is here. I think this one, yeah, like nobody has the compost ones out, so this one just passes us all. If you define a text-based language, you have to define a syntax. Both amateur and professional language designers categorically underestimate how difficult this is to do. Defining a grammar that makes parsers happy is easy. Defining that one that makes users happy is hard. Syntax design is user interface design, and that process doesn't get easier when you constrain the user interface to a string of characters. You have to implement a parser. Despite the reputation, this part is pretty easy. Either use a parser generator like Antler or Bison, or like I do, hand roll a little recursive descendant one and you're good to go. You have to handle syntax errors. This is one of the most important and most difficult parts of the process. When users make syntax and semantic errors, which they will constantly, it's your job to guide them back onto the right path, giving helpful feedback isn't easy when all you know is that your parser is sitting on some unexpected punctuation. It will likely turn off non-technical users. We programmers like text files. Combined with powerful command line tools, we think of them as the Lego blocks of computing. Simple, but easily composable in a million ways. Most non-programmers don't think of plain text like that. To them, text files feel like filling in tax forms for an angry robotic auditor that yells at them if they forget a single semicolon. Yeah, that's true. And that's the way I think. Yeah. So then the next section is the way that the author is suggesting that we do this. If you define a graphical authoring tool, you have to implement a user interface, buttons, clicks, drags, stuff like that. Some cringe at the idea of this, but I personally love it. If you go down this route, it's important to treat designing the user interface as a core part of doing your job well, not just an unpleasant task to be muddled through. Every little bit of extra work you do here will make your tool easier and more pleasant to use, and that directly leads to better content in your game. If you look behind many of the games you love, you'll often find the secret was fun authoring tools. You have fewer error cases. Because the user is building behavior interactively, one step at a time, your application can guide them away from mistakes as soon as they happen. With a text-based language, the tool doesn't see any of the user's content until they throw an entire file at it. That makes it harder to prevent and handle errors. Portability is harder. The nice thing about text compilers is that text files are universal. A simple compiler just reads in one file and writes out one. Porting that across operating systems is trivial, except for line endings and encodings, of course. When you're building the UI, you have to choose which framework to use, and many of those are specific to one operating system. There are cross-platform UI toolkits too, but those often get ubiquity at the expense of familiarity. They feel equally foreign on all of the platforms. So then there's the see also. So then, okay, the pattern is close sisters. The game forms interpreter pattern. In fact, you often end up using both patterns. The tool used to generate bytecode. Okay, yeah, so you'll use the interpreter pattern to generate the bytecode from your graphical tool, which then you use the bytecode in sort of this system here in our VM that we have over here on the left. The Lua programming language is the most widely used scripting language in games. It's implemented internally as a very compact register-based bytecode VM. Kismet is a graphical scripting tool built into the Unreal Engine, the editor for Unreal Engine. My own little scripting language, Ren, is a simple stack-based bytecode interpreter. Okay, that's cool. I'm thinking, I'm not going to implement this for the game that we're going to use to implement as many of these as possible. But what I do want to do is this could be like a future meetup talk or conference talk that I do where I maybe implement this. And so maybe we can create a game in the future that does this. So I'm going to think about games that I can do, and I'm going to add that into the project list. And so the same that I did with the observer pattern, where I did that in Rust, and I've also done that in JavaScript. I'll probably do this same thing, but this is gonna be a lot bigger. So that'll probably be maybe a future project that's gonna come down the stack. So I'm gonna add that into my to-do list. Until then, I am gonna go ahead and forward us on. So there's 30 of us here. So I have to get ready and go to my my stand-up and do my entire programming day today. So let's see who we can raid.